Okay, so now that we have gone through all the rational function stuff or rational expression stuff, now we can start working with rational functions. So a rational function is, of course, a function, and it's a function of the form f of x equals p of x over q of x, where p and q are polynomials. So it's just like it's a rational expression, but now we're making it into a function. And you can write it in a million different ways. You can write it as y, because remember, y and f of x are synonymous. They mean the same thing. So y equals 1 over x, that's an example of like the most quintessential rational function. But then you also have things like more complicated ones like 5x minus 4 over x, where x to the fourth plus 2, or x plus to the fourth plus x minus 2. You can also have constant rational functions. 1/4, because 1 and 4 are technically polynomials, 1/4 is technically a rational function. And then also, technically speaking, any polynomial function that we had, like x squared plus 3x, you can write that all over 1 and treat it like a rational function. So we're going to be studying, this is a natural extension of what we've been doing. We were talking about polynomials and we learned all this fun stuff about them. And now we can expand upon that and talk about rational functions, which are polynomials over polynomials. So when it comes to domains and intercepts, we're going to be studying all the different properties of these things. The first one is domain. The domain of a rational function. This is not anything new. We've already seen this. It's all real numbers except numbers that make what? They would make q of x equal to 0. So we've already done this. We did this on exam 1, where if you had something, we would set the denominator equal to 0 because we don't want to be dividing by 0. That's a problem. So much like before, trying to find the range of a function without its graph is quite difficult. So we'll leave the graphing to find ranges, but that's it. So the x-intercepts are found like normal. It is the same process. That is, you're going to set y equal to 0. But that is, we're trying to do p of x over q of x equaling 0. Sorry, let me add one more thing, actually. That is, f of x equals 0, which implies that p of x over q of x is equal to 0. Because f of x, a rational function, is a polynomial p over a polynomial q. If you're setting y equal to 0, that's the same thing as setting the function values equal to 0, setting f of x equal to 0, and solving that equation for x. Now, where would this, like, how would I set this equal to 0? Like, where would I get the zeros from? Would I get it from p or would I get it from q? This will only, you'll only get 0 if the numerator equals 0. Right? That's the only way that could happen, which can only happen if p of x equals 0. The numerator equals 0. Because if the denominator equals 0, you're dividing by 0, and that's a big no-no. That can't happen. That's where the domain comes into play. But for x-intercepts, that would only happen, you only get that the function equals 0 if the numerator equals 0. So in practice, all you need to do is set the numerator equal to 0 to find the x-intercepts. So that's what I'm going to do shorthand in a little bit. But here's a cautionary tale. Make sure these, make sure the x values are in your domain, are in the domain. You'll see an example of what happens with this in the second example below the example on the right, but that's what's going to happen. So make sure that when you solve this and set it equal to 0, you might end up getting a value that is both a zero of the numerator and a zero of the denominator, which we'll talk about in a second. And then the y-intercepts, they're found like normal. Just like before, you're going to set x equal to 0, which implies f of 0 equals blah. If you're setting x equal to 0, that means you're plugging 0 into the function, which is the same thing as evaluating f of 0. Okay. Let's see it in action. Let's do the first example. F of x equals 2x squared minus 6 over x plus 5. So, for the domain, we need x plus 5 to not equal 0, which means that x cannot equal negative 5. So this is nothing new. We've already seen this. We saw this on exam 1 on page 2, or page 3. I think it's technically page 3, is the second page of work that you needed to do. And we had a question that was talking about domain, and you needed to factor. Well, we'll see like a closer example that was on the exam with part B. So this is nothing new. We haven't learned anything new. It's the same thing, but we're applying it to a new situation, like when we're learning all about rational functions. So I know immediately the domain is parenthesis negative infinity to negative 5, parenthesis union, parenthesis 5 to positive infinity. But if that's still struggling for you, you can always draw a number line to help you visualize this. The number line would look like this. Here's negative 5. That value needs to be plucked out, and everything else is fair game. Everything except for this value. That's why it's negative infinity to negative 5 union 5 to positive infinity. You don't have to draw a number line. It's just there if you need the visualization. Any questions on that? Tina.
For the domain, wouldn't it be negative 5 to positive infinity? Or
Negative 5 to positive infinity. I think I said negative. Yeah, please make that a negative sign there. Yeah, but they do. They totally do. Thank you for catching that. And then the x-intercepts. So technically speaking, you're setting y equal to 0. You're setting the function equal to 0 and solving for it. But with a rational function, that only happens if the numerator equals 0. So I'm going to skip the middleman and just say numerator equals 0. Which gives me 2, and I'm going to factor 2x squared minus 6 equals 0. And that factors to 2 times x squared minus 3 is equal to 0. You can factor out a GCF of 2. And then remember, anything can be a difference of squares if you really want it bad enough. So yes, 3 is not a perfect square, but you can write it as a square. So you can factor this to x plus the square root 3 times x minus the square root of 3 equaling 0, which gives me x equals negative square root 3 and positive square root 3. Because remember, the 2 doesn't give me any zeros because it's just a 2. So by the zero product rule, either 2 equals 0, which is ridiculous, x plus the square root of 3 equals 0, which is where I get the negative square root of 3, or x minus the square root of 3 equals 0, which is where I get the positive square root of 3. So we have the x-intercepts plus or minus the square root of 3 comma 0. So it's not wrong to start this off by setting the whole, like this is what you would probably want to do in short, is 2x squared minus 6 over x plus 5 is equal to 0. But that just means that 2x squared minus 6 is equal to 0. That's the only thing you need to solve. Setting the denominator equal to 0 won't give you any zeros. It won't give you any places where the function equals 0. So it'll just give you where the function's undefined. All right. Next, we'll find the y-intercept, if it has one. The y-intercept is going to be found by just finding f of 0. So f of 0 would be equal to 0 minus 6 over 0 plus 5, which is negative 6/5. So our y-intercept is 0 comma negative 6/5. On Alex, it just wants you to write the number portion. So it would accept plus or minus the square root of 3 and negative 6/5. Okay. Any questions on that? Okay. For the next function, r of x is equal to 2x squared plus 4x minus 16 over x squared minus 4. For domain, very, very similar. Like it's the exact same thing, but instead of dealing with a linear denominator, we're dealing with a quadratic denominator. We need x squared minus 4 to not equal 0, which is the same thing as saying x plus 2 times x minus 2 cannot equal 0, which gives us x can't equal negative 2 or positive 2. So if you can figure out the domain from that information alone, that's awesome. But you can also draw a number line. The domain should be negative infinity to negative 2 parenthesis union parenthesis negative 2 to 2 parenthesis union 2 to positive infinity, all with parentheses. But once again, if you need to see a number line to figure it out, here's negative 2 and 2. Those values need to be plucked out. And everything else in between and outside is fair game. Draw the number line if it helps, but you don't need to. So the only issues are negative 2 and 2. Now we'll find the x-intercepts. You're setting the numerator equal to 0. So we've got 2. I'm going to factor out a 2 right from the start. We've got x squared plus 2x minus 8 equals 0. And that factors nicely. 2 times x plus 4 times x minus 2 equals 0, which gives us x equals negative 4 and positive 2. And John Doe student boxes that answer in. Why is John Doe student going to get marked off 1 point? Because it can't be 2. So I'm gonna highlight this one and cross it out. This is not in the domain. Two is not part of the domain of the function. It's going to be a problem for this one. If you plug in 2, you're going to get 0 in the numerator and 0 in the denominator. That means that it's indeterminate. If you guys remember, there's a difference between indeterminate and undefined. If it's dividing by 0 and that's it, like 5 divided by 0, 10 divided by 0, negative pi divided by 0, that's undefined. There is no mathematical value. 0 divided by 0 is indeterminate. So now we're going to finally get to see a situation of what it means for it to be indeterminate. What does that actually mean on a graph? And we'll get to that in a second. So there's only one x-intercept. It's negative 4 comma 0 only. And then the y-intercept is found like normal. It's r of 0, which in this case would be 0 plus 0 minus 16 over 0 minus 4, which is going to be positive 4. So that's going to be 0 comma 4. We'll talk about what's going on with that too in this function in just a little bit. But in order to talk about it, we need to talk about we need to talk about asymptotes. So are there any questions on what we've done so far? So finding the domains, no different. You're setting the denominator equal to 0 to find out where the function doesn't exist, and then plucking those points out. X-intercepts are the exact same. You're setting the function equal to 0, but they can only equal 0 if the numerator equals 0. But the only extra caveat that we have to do is make sure that's actually part of our domain. So this time it was not. And last but not least, the y-intercept is still found just like we found it before. You're setting x equal to 0, but that's the same thing as plugging in 0 into the function. So one thing that polynomials don't have that rational functions do have are what we call asymptotes. The P is silent like in pterodactyl, right? It's a silent P, and it's pronounced asymptote, not asymptote, because it's not a P at the end. It's an asymptote. And my wife gets on my case every time, so I have to get on your guys' case every time because she's very, very particular about that. That's the hill she's willing to die on, and because by extension, I make that problem on you too. So it's an asymptote, not an asymptote. A vertical asymptote is a vertical line. And so a vertical line is an equation. And do you guys remember what is it x equals or is it y equals for a vertical line? X equals. Because vertical lines aren't functions, so they can't be written as y equals. That's the horizontal lines. But they're vertical lines, x equals c. That's I meant to say this beforehand. The formal definition of a vertical asymptote requires calculus notation in order to get we need the concept of limits, which we don't have in this class. But we can still talk about them intuitively and get kind of a rough definition to get our understanding, because we just need to be able to find them, and that's about it. So they are a vertical line that splits the graph locally, so where we can see it usually. In particular, as your x values get closer and closer to c from either the left or the right, you'll see that the function values, the y values, will get infinitely large in either the positive up direction or the negative down direction, because your y values go up or down. Now, as an important little aside, something to remind ourselves is that if we have a number divided by a big number, this will be approximately 0 versus a number divided by a small number equals a big number. The smaller the denominator, the bigger the overall fraction, the bigger the overall value. This was that I think I told you guys about it, but that whole kind of silly thing that showed that Americans are dumb, right? A&W, the root beer company, they still have them around every once in a while. They have food franchises where you can buy burgers and stuff, and they were trying to compete with McDonald's at the time, and so they introduced their own third-pound burger. It had a third pound of beef instead of a quarter pounder, which only had a quarter pound of beef. So a third is larger than a fourth, but Americans saw 3 smaller numbers, so 1/3 smaller than 1/4. So it was a smaller burger, so it failed as a campaign. They didn't expect Americans to be bad with fractions, and that was their fault. But point being is that the bigger the denominator, the smaller the overall number. Think about if you have 1 divided by 100, that's 0.001. So if you get a very, very big number in the denominator, that basically goes to 0. And if you have a very, very small number, think about dividing by 1/2. If I don't write this down, but if I have 2 divided by 1/2, that's a number very, very close to 0. It's a very small number. That ends up being 4. If I take 2 and I divide it by 1/3, 1/3 slightly smaller than 1/2. It's 0.33 instead of 1/2. So that's going to be 6. If I do 2 divided by 1/100th, which is 0.001, that's a very, very, very small number. That's going to equal 200. So the smaller the denominator, the bigger the overall number. Keep that in mind as we talk about vertical asymptotes. Then, oh, and by the way, from now on, we're going to write vertical asymptote. We're going to write VA. So that we don't have to keep writing vertical asymptote. That takes way too long to write. Then a horizontal asymptote, which we're going to abbreviate HA so that we don't have to write it. A horizontal asymptote, an HA, is a horizontal line, and horizontal lines are of the form y equals a number. I'm going to call it L. C and L are arbitrary names that I decided upon, or mathematicians decided upon. I don't know why they chose C. I know why they chose L, and it has to do with limits, but I'm neither here nor there. And these horizontal asymptotes, they describe end behavior of your function, the stuff that's happening when x gets incredibly large. Whether it be positive or negative is irrelevant. So it's what it's telling you is that your y values, your function values, are leveling off as your x values get infinitely large in the positive or negative direction. So in this example, see, this is the value C, this is the value L, and so this is the HA, y equals L, and this is the VA, x equals C. Ha. Looks like ha. Ha. Okay. And so a couple things I want you to notice about these things. Notes. Number one is that functions, quote unquote, hug their asymptotes. You'll see as we get closer and closer to this vertical asymptote, your function starts to try and get closer and closer to it on either side of C. When we approach C from the right-hand side, from the numbers that are more positive, you see that your function starts to hug it closer and closer, but it goes down towards negative infinity. And then as we keep going further and further out, you see that your function values start to level off and hug the horizontal asymptote. That's how they work. They are tendencies of your y values. The other thing is that since HAs deal with end behavior, a function can cross its HAs. But a function cannot cross a VA. Let's write that down and then we'll explain what's going on here. So, talked about the hugging thing. So then horizontal asymptotes. So horizontal asymptotes have to do with what's happening very, very, very far out. So it is fine for your function to cross over a horizontal asymptote. It doesn't happen very frequently, but it does happen enough so that I want to mention it's okay for your function to do that. In fact, I even have in my calculus course, I give them a problem that has a graph that looks like this. like that. It's possible for you to cross over your horizontal asymptote infinitely many times because it has to do with what's happening at infinity or negative infinity. But vertical asymptotes have to do with local behavior. And so you can't have these two functions connecting here because if you did, the only way you could connect them would be with a vertical line. And if there's a vertical line there, it's no longer a function, right? So in particular, functions don't exist at their vertical asymptotes. So as a small thing, like we can say f of c does not exist, doesn't exist. F of c does not exist, and that will actually get us some important information on how we find vertical asymptotes. Okay, so how do we find them? I gave you a picture of them, but I didn't give you anything about how to find them. What you're going to do is you're going to factor the numerator and denominator, and then you're going to cancel any common factors. If a factor gets completely wiped out or canceled out, then there will be a hole in the graph where that factor equals 0, called a removable discontinuity. If you study complex analysis, if you study complex numbers, we call it a removable singularity, which sounds way cooler, but removable discontinuity is fine enough. So this example right here, f of x equals 2, you can factor out a 2x. So I'll rewrite it, 2x squared plus 6x divided by x squared plus 4x plus 3, and that factors to 2x times x plus 3 over, this factors to x plus 1 times x plus 3. And so the x plus 3's get canceled out, completely canceled out. So suspend disbelief for a second. We'll explain why the hole happens and what's going on in just a moment. But because the x plus 3 got completely wiped out, there is going to be a hole in the graph where that factor equals 0. So in particular, there's a hole in the graph at x equals -3. So this new, this is what I'm going to call, so it's going to be 2x over x plus 1. This is the new denominator. Okay. Any questions so far? Where that factor gets completely canceled out, or if a factor gets completely canceled out, there's going to be a hole where that factor equals 0, so in this case, -3. So, step 2. Now that we've canceled out any common factors, we found out we've got a new denominator. Vertical asymptotes will occur wherever the new denominator equals 0. You can find the y-coordinate of the hole of any removable discontinuity by plugging in the x value of the hole, x value of the hole, into the simplified rational function. So VA, where the new denominator equals 0, that's going to be x plus 1 equals 0, which gives me x equals -1. That is my vertical asymptote. This curve, this rational function, has one vertical asymptote at x equals -1. I'm going to draw a graph just for a second. You don't need to copy this graph, because we'll talk about how to graph a function in just a little bit. It's got a horizontal asymptote at 2. Wait. Yes, yes. So the curve looks like this. However, you'll see at -3, there's going to be a hole right there. Now the question becomes, how do I find out the location of that hole? Now, if I'm just graphing it with a rough sketch, I can just put the hole wherever. I don't need to have the specific value. But if we want to know exactly where it happens, the hole at x equals -3. So we're going to plug into into simplified version. So that is to say we've got 2 times -3 over -3 plus 1, which is going to equal -6 over -2, which is +3. So there's a hole at -3 comma +3. Doesn't make any sense. That doesn't make any sense to me. Because this function should look like that, but how is it at -3 comma 3? That doesn't make any. That's weird. That's weird. What is going on there? Oh, that's what's going on. That's the problem. That's the problem. This is not the correct graph. I'm sorry. That's a vertical asymptote at x equals 1. So sorry about that. I'm really, really sorry about that. That was a dumb, easy mistake, but either way. Sorry, what the graph should look like is instead like this. That's what it should look like. What I knew was wrong about that is that the purple line, the horizontal asymptote, should be at y equals 2, and we'll explain why that's the case in just a little bit. But how could that be below the y value of 2? It didn't make sense. So that's what I knew, but either way. Okay. So the question is, why do we have vertical asymptotes where the new denominator equals 0? And then also, why do we have holes where the factors cancel out? And furthermore, why do the holes occur? Why is it that we find the location of the hole by plugging it into the simplified version of the function? So let's answer that first question. Why do we get vertical asymptotes where the denominator equals 0? Well, imagine, so there's a vertical asymptote at -1. Notice that the function does not exist at -1. And as we get closer and closer and closer to -1, so let's say -0.9, right? Right here, -0.9. What we're going to get, if we plug it into the function, we get 2 times -0.9 divided by -0.9 plus 1. That's going to be -1.8 divided by -0.1, right? and we're taking a finite number, negative 1 point, we're taking a number and dividing it by a very, very, very small number. That's 1/10. And what do we see? If you take a number and divide it by a very small number, it becomes a big number. And that was just 0.1. I could do the same thing, but I could get even closer. I could do negative 0.99. And then this would become 0.01. And this would become 1.8, 1.98, I think. But it doesn't matter. But regardless, now I'm taking a number that's roughly the same thing, roughly the same. It's negative 0.98. And I'm dividing it by an even smaller number. So it's going to get even more big. Because we're dividing by a smaller number. Smaller the number, the bigger the overall value. Smaller the denominator, the bigger the overall value. And that's 0.9. We can keep doing this. And each time it's just going to get more and more and more positive. It's going to keep going up and up and up and up and up. The same thing is true for the other side, but you're going to have a positive over a negative, and it's going to be a negative over a positive. And it's going to be, oh, why am I doing negative? It should be positive. Down at the bottom. Sorry, we're approaching negative 1 from the right-hand side when we're doing negative 0.99, excuse me. But like, hopefully you see the idea is that we're looking for the places where the denominator equals 0, because as we get closer and closer to the places where the denominator equals 0, our denominator gets smaller and smaller, meaning that our overall y values will get larger and larger. So that's the answer to the first question. That's why we set the denominator equal to 0 to find the vertical asymptotes. They're the places where the derivative or where the function does not exist. Now the holes, why do they occur? And why do I have to learn this new thing? And the answer is because I want you to learn about them. No, it's not. It's because they have a cool concept to them. It has to do with how factoring works. Factoring and canceling works. So we talked about this in 0.8. We talked about that in the last section, 0.8 on rational expressions. So I've got a new example here to follow along with, but like look at x squared plus 8x minus 9 over x squared minus 1. You can factor the numerator and denominator, and then the x minus 1's cancel, and we end up with x plus 9 over x plus 1. But the thing that we frequently don't write, or we omit it for the reasons of it takes time to write, is provided x minus 1 does not equal 0, aka x cannot equal 1. That's the thing we typically don't write, because we're supposed to assume that we know that's true. But then we forget about it as we go along, and we don't write it. So let's analyze this a lot more. Because there are equal signs here and here, we are saying that these expressions are exactly the same. That means that they are equal for any value of x, except for that pesky x equals 1. So in particular, notice that if we plug in values that are really close to the issue value of x equals 1, we'll get the same outputs, because the only number that they have problems with together is 1. When you plug in 1 into this, you'll get 5. But when you plug it in over here, you get 0 over 0. If you plug in 1 in the left-hand side, you get 0 over 0, which is indeterminate. But if you plug in 1 on this side, you get 10 over 2, which is 5. So, point being is that's the only issue. So we plug in numbers really, 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 really close to 1, like 0.99 or 1.01. They will give you the exact same value. The left and the right-hand versions the unsimplified and the simplified versions will give you the same number. So for example, at x equals 0.9, the left side will give you 0.9 squared plus 8 times 0.9 minus 9 divided by 0.9 squared minus 1, and that will equal 5.21 dot 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 on forever. So remember, I'm plugging in 0.9. I'm not plugging in 1 because that would give me 0 over 0. I'm plugging in a number that's very, very close to 1. And if I plug it in on the right-hand side, the right side, I get 0.9 plus 9 over 0.9 plus 1, and that also equals 5.21 dot 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 dot. It's the same number. Which makes sense. They should give me the same number because the only place these two things do not agree is at 1. So, do you remember when we were doing piecewise functions, right? Don't draw this, it's just for reference. If this was the dividing value and like the curve looked like this, remember we plugged in the number into the function to find out what it should be at that value. Even though it doesn't exist at that, one idea is that you can keep trying to plug in numbers really, really close to that value and see what it approaches. The same thing is true here. So that is to say, the simplified version tells us what the value should be at x equals 1. This is better explained in calculus in the first unit when we talk about limits. But we don't have calculus knowledge right now, so we can't go into that. But what I want you to understand is that the right-hand side tells you what it should be. If you could plug in 1, here's what the value would be. That's what it's doing. The simplified version is saying, if you could plug it in, which you can't because you get 0 over 0, but if you could, you would get 5. And so that's how we find the holes. We plug them into the function's simplified version because that tells you what it would look like if it didn't get 0 over 0. So that's what an indeterminate value is once you get context, the context here being that the original function is this and its reduced version is this. Given that context, that 0 over 0 will equal 5. It is now a determinable value because of the context that we're in. It still doesn't actually exist in the real function. 0 over 0 isn't actually a value, but you can figure out what it's approaching, which is 5. So let's look at some examples of this. Find the vertical asymptotes of the following functions. So we don't care about the numerator at all, but we still need to factor it so that we see anything. So this is x plus 3 times x plus 5 divided by, there's a common factor of 7, and it's x squared plus 2x minus 35. And that factors nicely. The numerator I've already factored to x plus 3 times x plus 5, but the denominator will look like x, so it's 7 times x plus 7 times x minus 5. And use whatever methods you want to factor, your choice. Two numbers that multiply to negative 35 and add 2, that would be positive 7 and negative 5. That's why it's x plus 7 and x minus 5. Now, it may be tempting to want to cancel out the x plus 5 and the x minus 5, but that doesn't happen because they're not the same term. They're not the same factor. So no cancelizations. No cancellations. So no holes. You can think of maybe if it helps you think about like if somebody cancels, then you got an open slot, right? If you are if you're trying to go to a restaurant and somebody cancels their reservation, that slot now becomes open, an open circle. Just thought of that. Maybe it helps, maybe it doesn't. Who knows? So there's going to be no holes in this graph because nothing canceled. So we just go on to VAs. VAs where the new denominator, and I'll put new in quotation marks. The reason why I put the new in quotation marks is because nothing canceled. So the new denominator is the old denominator. So that can happen. So that's setting 7 times x plus 7 times x minus 5 equal to 0, which gives us x equals -7 and +5. Those are our vertical asymptotes. They are x equals. They have to have an x equals, otherwise they're just a number. As soon as you say x equals that, that is talking about the equation of a vertical line. I guess technically I should write it as x equals -7, comma x equals 5 because they choose, but x equals -7 and 5 is fine enough. Okay. The next one, we'll factor it. Unless there's any questions on this or on the whole section. I realize I should have stopped for any questions if there were about why holes, why removable discontinuities occur. Okay. We'll do this next one, and then we'll take our break. So q of x equals x cubed minus 25x over x cubed minus 10x squared plus 16x. So let's factor the numerator and the denominator. I see that both of them have a common factor of x. So in the numerator, it becomes x times x squared minus 25. And in the denominator, it becomes x times x squared minus 10x plus 16. And yes, you could cancel the x right now if you wanted to, but I'm going to wait until everything's factored just to make it look pretty. It's not wrong to do it now, though. But this thing is x times x plus 5 times x minus 5, all divided by x times x minus 2 times x minus 8. So the x's will cancel. And this becomes equal to x plus 5 times x minus 5 divided by x minus 2 times x minus 8. And because the x is canceled, there's going to be a hole at x equals 0. Because the x got completely canceled out, there will be a hole at x equals 0. And in particular, it happens by plugging 0 into this simplified version. So 0 plus 5 times 0 minus 5 divided by 0 minus 2 times 0 minus 8. That's going to equal -25 over 16. So there is a hole at 0, -25/16. That's part of the answer, but not the full thing. But once again, so we have a hole because x got completely canceled out, so a hole at x equals 0. And to find the location, we have the x value. To find the location of the y value, where the hole should happen, we're going to plug it into the simplified version and get negative 25/16. So that's where the hole's y value should be. We plug in x, we get a y. That's a hole. And then the VA, the vertical asymptotes, they should happen from setting the denominator, the new denominator, equal to 0. X minus 2 times x minus 8 equals 0. That gives me x equals 2 and positive 8. So vertical asymptotes of 2 and 8. So this thing has two vertical asymptotes and one hole in the graph. Any questions on that? Good? Okay. Let's take our break. Let's come back at 12:05, 12:04, 12:05, 12:05. People watching recording do some guided meditation and some squats. I don't know. Okay, so that's how we find vertical asymptotes, which is setting the new denominator equal to 0. If anything cancels out, you get a hole. Now we talk about horizontal asymptotes. Now, the key thing to understand is that horizontal asymptotes deal with end behavior. And do you remember what we looked at with end behavior of a polynomial? What decided the end behavior of a polynomial? Do you remember? What? Um, the y values will determine the end behavior, but in particular, it comes from the leading term, right? To look at for a polynomial, you look at the leading term. But this time, we're not dealing with just one polynomial, we're looking at both polynomials. So you're looking at the leading term's degrees. And so every textbook has this as a three-part theorem, essentially, and a thing that you need to memorize, but I'll show you how you don't necessarily need to do that. If the degree of the numerator is less than the degree of the denominator, then there is an HA, there's a horizontal asymptote at y equals 0. So looking at this one, the numerator is degree 1, and the degree of the denominator is degree 8. So there must be an HA at y equals 0. So one way we can think of this, the intuitive reason, we'll wait until we get done with all of these examples, and then we'll talk about the intuition. So if the degree of the numerator is equal to the degree of the denominator, if they both have the same degrees, then there's an HA at what we call the y equals the ratio of leading coefficients. So a ratio is a fraction, and the leading coefficients, those are the number portions on their leading terms. So it's a fraction of their leading coefficients. So in particular, we notice that these are both degree 5. And then what I'm going to do is I'm going to highlight their leading coefficients. Because they are the same degree, the degree of the numerator equals the degree of the denominator. That means that there's a horizontal asymptote. In particular, it's a horizontal asymptote at y equals 17 divided by 3. Those were the leading coefficients. 17 was the leading coefficient in the numerator. 3 was the leading coefficient in the denominator. And last but not least, if the degree of the numerator is greater than the degree of the denominator, then there is no HA. If the numerator is a bigger degree, then there is no HA. So looking at this one, you're looking at the degrees of the numerator and denominator. The numerator is degree 4, the denominator is degree 2. So the numerator has a bigger degree, so there is no HA. So I want to give an example of what, like, the intuition as to why this is, because you can memorize this as a fact. And the more you do this, honestly, you probably will have it memorized just by pure amount of practice. But I want to explain why. We're talking about really, 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 really large positive values and really, really large negative values of x when we're talking about end behavior. So we're talking about infinity, which is a concept, not a number. So if we just look at a small number compared to infinity, 10,000, right? X to the 6th, the leading term here is approximately 10 to the 24th. It's a very, very large number. And x to the 4th, or x squared here in the numerator, that one doesn't matter. So x to the 4th is 10 to the 16th, meaning that x to the 6th is 10 to the 8th times larger, or 100 million times larger than x to the 2nd power. So that's just 10,000. What about, so thousands, millions. What about 100 billion? The difference is just going to keep getting more and more staggering. So when we're looking at infinity, these things are basically gone. They don't really matter in the long run. And so what we have is this equal ratio of an x to the 6th over a 12x to the 6th. This function has an HA at y equals 1/12. Because at the end of the day, when we plug in these absurdly large numbers, nothing other than the leading terms matter, and they're both increasing at the exact same rate. They're both increasing at a very, very they're all like the same rate. So we'll have basically 1 million to the 6th over 12 times 1 million to the 6th. The 1 million to the 6th cancel, and we just have 1 over 12. That's what's happening, is that all the smaller numbers don't really matter. All the smaller powers of x don't really matter. And another way you can verify, I'm going to write quote unquote check your work by plugging in large values of x. So people watching the recording, you won't be able to see this. I'm going to pause the recording, in fact, just to get this going so you can see it. But people watching the recording, if you want to know, just come talk to me before or after class, and I'll get in action. Does anybody have any questions on that, or are we ready to do some practice problems? All right, looking at this first one, find the horizontal or asymptotes of the function if they have one. So this one here, 3x cubed plus blah, blah, blah over 4x to the 4th. Looking at the leading degrees, if you want to appeal straight to that little fact up above, then you would just say the degree of the numerator is less than the degree of the denominator, which implies there's an HA at y equals 0. If you want to do the intuitive approach, think about the fact of the matter is, when I plug in a number like 1,000, which isn't even close to infinity, right? Infinity is way larger than that. It's not a number, but you get the idea. We could go even further. We could go to 10 billion. We could go to 10 trillion. But let's work with a number that's a little more approachable, 1,000. If you plug in 1,000 into this expression, remember, none of these matter. None of these small terms matter. And if you're looking at this, if you plug in 1,000, the denominator is 1,000 times larger than the numerator. So you've got a number divided by a large number, which is approximately 0. And that was just 1,000. What if we plug in 10,000? If we plug in 10,000 for x, this number here is 10,000 times smaller than this number. So basically, this is going to be 1 over 10,000, roughly. Then we could go to a million, and then it'll be roughly 1 over 1 million, and then it'll be 1 over 1 trillion as we get closer and closer to infinity. So it just basically keeps getting smaller and smaller and smaller until it's virtually 0. That's the concept of a limit, but we don't need to do that yet. Next one, B. And also, if you use your calculator on that one, if you plug in 10,000 or 1,000, honestly, 1,000 should be enough. Use your calculator, plug that in. You'll see that you get roughly 0. It'll be something very, very small. Then with this one, 12x to the 5th over x cubed minus 7x squared plus 8. The degree of the numerator is larger. The degree of the numerator is greater than the degree of the denominator. So that means that there is no HA. By a very, very similar argument. If you plug in 100, or let's just do 10 for a second. When you plug in 10, this number will be 10 squared times larger than this number. It'll be 100 times larger. And that's just at 10. Once you plug in 100, it'll be 100 squared, which is 10,000 times larger. So when we plug in 100, we're already 1,000 times larger in the numerator than we are in the denominator. Then we plug in a billion, a trillion, and it just keeps getting a more and more of a substantial difference. And you can see that on the calculator. So this is where we have to be a little bit careful. So I'm going to pause the recording so people can't. So that's how we can check to make sure something is an HA, just by plugging in several different power, like numbers that are very large for x, and see if it's tending towards, if it's like leveling off at all. And then the last one, if we're looking at this one, the degree of the numerator and the degree of the denominator are both degree 2. Degree of the numerator equals the degree of the denominator. So that means that there's an HA at y equals 2 over negative 3, which is negative 2/3. And this time, it's because they're increasing at the exact same rate. The x squared and the x squared. Everything else doesn't matter. So when you plug in 100, the 100 squareds cancel, and you just have 2 divided by negative 3. No matter what you do. You plug in 2 billion, you got 2 times 2 billion squared over negative 3 times 2 billion squared. The 2 billion squareds cancel, and you still have that ratio of 2 over negative 3. Any questions on that? Okay. One thing that you might be wondering is, well, what happens in the case where you don't have a horizontal asymptote? Does that just mean that the function goes off to infinity and they calls it good? We don't have any other stuff? Well, there are a few cases that you can look at, and that would be an oblique or a slant asymptote. Some textbooks call them oblique asymptotes, some call them slant asymptotes. So we'll use them interchangeably. And if the degree of the numerator is exactly 1 more than the degree of the denominator, your rational function won't have a horizontal asymptote because the degree of the numerator is larger. And that means that the numerator grows faster. So you get a big number over a finite number, it becomes infinity. But rather, it will have a slant / oblique asymptote, or an oblique / slant asymptote. So I'm going to call that an OA or a SA. An oblique asymptote OA or a slant asymptote SA. Further, this asymptote, well, how do we find it? So looking at the graph, this is your OA right here. So your OA, And it's going to be of the form y equals mx plus b. And how do we find it? How do we find it? This asymptote will be the quotient, will be y equals the quotient from the division. And note that just like like oblique asymptotes, they deal with end behavior as well. They deal with end behavior as well. And I'll explain why this is true. Why does this happen? And in fact, you can actually keep going with this, but it becomes a little more difficult the higher the degree because, once again, we saw lines are always going to be lines. There's no, it just shifts and it's always a line. And quadratics are always the U shapes, right? But once you start getting to cubics, you can either have this or you can have this. And then with quartics, you can either have this or this, or you can even have this, and you can even, and then with degree fives, it just keeps getting more and more complicated. But point being is, if the degree of the numerator is exactly 2 more than the degree of the denominator, you have not an oblique asymptote or a slant asymptote, you have a parabolic asymptote. So what it looks like is on your graph, it will follow a parabola instead. It'll have like a parabolic asymptote, which is pretty cool when you think about it, that it does that. But I digress. So find the slant or oblique asymptotes of the following rational functions. H of x equals 3x squared plus 10x plus 6 over x plus 2. So the degree of the numerator, the degree of num is exactly 1 more. And that implies there's an OA. I believe our book uses oblique asymptote, but other books will say slant. So, in particular, this means that we have to do, we can use synthetic. Right? Because we're dividing by x plus 2. So should it be 2 or negative 2 for the synthetic? Quick, negative 2. Joy is exactly right. It was Joy that said that, right? Yeah. Because remember, this is x minus negative 2. So our C value in the synthetic division is negative 2. So we'll set that up. Negative 2 divided into, and notice that all powers of x are present in the dividend, the thing up top. 3x squared plus 10x plus 6. Draw a vertical line. Bring down the 3. Multiply diagonally, add vertically. So negative 6, 4. Negative 2 times 4 is negative 8. And then negative 2. So this gives me the OA. OA at y equals 3x plus 4. That is our answer. That's how we do it. Okay, but why though? Why? And here's the reason. And you don't have to write the reason, but if you'd like to know. If you remember the division algorithm, what it states is that if you divide a polynomial by another polynomial, you get, so if we have 3x squared plus 10x plus 6 divided by x plus 2, it's equal to its quotient, which is 3x plus 4, plus our remainder, negative 2, divided by our divisor, x plus 2. Right? That's what the division algorithm says. And because the degree of the numerator is exactly one more, and remember what we learned when we were talking about 2.3, when we were talking about division of polynomials, the quotient's degree is always the difference of the degree of the numerator and denominator, right? Do you remember that? If you take the division of the numerator divided by the denominator, the quotient will always have a degree equal to the difference. 2 minus 1, degree 1. 3 minus 2 in part B, it'll be degree 1. It always is. And so, what's the point? As x goes to positive infinity or negative infinity, the negative 2 over x plus 2 goes to 0. So, at infinity, 3x squared plus 10x plus 6 over x plus 2 is approximately 3x plus 4. So now that you've written that down, let's talk about it. Let's talk about what's going on. Now that you've written it. By the division algorithm, when you divide 3x squared by 3x squared plus 10x plus 6 by x plus 2, you get a quotient, 3x plus 4, plus negative 2 over x plus 2. These two things are the same. They're equal to each other. But what I'm telling you is that as x gets infinitely large, right, this will effectively be 0. Go ahead and plug in 98, and you'll see that it's negative 0.02. Plug in 998, and this will be negative 0.002. And that's just 998. Think about 9,999,998. Then that number will be even smaller. So at infinity, when you're looking at really, 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 really big numbers of x, these two pieces are effectively 0 because it's like this thing is just nothing. So the function should look like 3x plus 4, the line. So that's what's happening. It's becoming almost equivalent to that line. That's what's happening. Any questions on that? Man, I gotta say, I do love these ones as a good as a good example of practicing your long division. Maybe one of those things might show up on the exam. Maybe just finding an OA, finding a slight asymptote. Maybe that might be something you might need to know, hypothetically. We all see the wink. Maybe we need to know how to find an oblique asymptote on the exam. Maybe. Anyways, this one, y equals 2x cubed plus 7x squared minus 10 over x squared minus 3. The degree of the numerator is exactly 1 more than the degree of the denominator. Same thing. So it has an OA. We can't use synthetic, though. Sad days. So we'll have to do long division. X squared minus 3 divided into 2x cubed plus 7x squared. Uh-oh, there's no power of x, the first power. So we need a placeholder. So plus 0x minus 10. I'd like you guys to go ahead and complete the long division because it's good practice. We're going to need to do that on the exam. We might even need to do it on the final at some point. So it's good practice getting ready for our upcoming exam. Speaking of which, well, I'm going to pause the recording. People watching the recording, go do it as well. Do the long division. All right, so this is what you get for the long division. You should get 2x plus 7 is your quotient with the remainder of 6x plus 11. Once again, I'm going to say this because I'm hoping everyone remembers. Remember, you're subtracting a collection of terms, so that minus sign needs to get distributed. That's why it becomes plus 6x, not minus 6x, because you're subtracting a negative 6x. And the same thing goes here. You're taking negative 10 and subtracting negative 21. So that's really adding 21. That's why it's plus 11. But honestly, we don't really care about the remainder because the remainder doesn't really do anything for us in this problem. But what I want to, like, you can write this if you want to, but just to visualize it again. So 2x cubed plus 7x squared minus 10 divided by x squared minus 3. By the division algorithm, this is 2x plus 7 plus a remainder of 6x plus 11 divided by x squared minus 3. And as x goes to really, 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 really big numbers, 6x plus 11 over x squared minus 3 is virtually 0. So at very, 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 very large values of x, both positive and negative, this function, your function, is approximately equal to 2x plus 7 because this will be negligible. There's almost no difference between the two of them. That's the reason why an OA occurs. Okay. So now the question, this is how you get your third date, is now you can learn how to graph rational functions. Once you get this, you can ensure that you get a third date, maybe even a proposal, maybe a proposal, not guaranteed. I'd say 80% chance. With all the students that have done it for me, 80% have done it. 0%, 0 people, that's still 80% though. So we're calling good. Has anybody tried it yet? Isaiah, have you tried it on any dates? Using the polynomial graph to get a second date? No. Keena? No. Okay. Well, maybe one day. Maybe one day. Okay. Just need more data, guys. I need more data. Graphing rational functions. How do you graph one? So, step 0. This is something I always recommend because when I want you to take into consideration, when we were looking at horizontal asymptotes, were we looking at the factored form? No, we were looking at the expanded form, the standard form of it. But when we were looking for domain and looking for vertical asymptotes and holes, we cared about the factored version. So both versions tell us some information, just like with polynomials, right? Remember with polynomials, we liked seeing it in standard form because that gave us end behavior. I'm going to go back to it for a second so you can see that. 2.2. We liked seeing it in standard form because standard form gave us the end behavior. And then we liked seeing it in factored form because the factored form gave us the zeros and their multiplicities. In a very, very similar fashion, when it comes to rational functions, the standard form and the factored form give us additional pieces of information. So what I like to do is I like to write next to it, and this is what I will do on exams. If there's ever a problem that involves dealing with a rational function and answering questions about it, I will give a bunch of extra space up here so that you can write it in both its standard form, its factored form, and if necessary, its simplified form as well. So this thing factors to 2x over x minus 3 times x plus 1. And there's no cancelizations, so no holes. No cancellations, so no holes. This helps with all other steps because if you're finding the domain, that really needs to be, that comes from the denominator. And now you already have it factored. So for the domain, we need the denominator to not equal 0, need x minus 3 times x plus 1 to not equal 0, which means that x can't equal 3 or negative 1. So hopefully you can create the interval notation for that right from just looking at it. But if you can't, always draw a number line. It never hurts. I'm going to still do it. So I'm going to still draw a number line. So here's negative 1, here's 3. You got to pluck those two values out. You cannot equal those, but everything else is fair game. So the interval notation for the domain is parenthesis negative infinity to negative 1 parenthesis, union parenthesis negative 1 to 3 parenthesis, union parenthesis 3 to positive infinity, end parenthesis. I'm not going to box it in because that's not actually the answer. The answer is going to be drawing the graph. Then we need to find the intercepts, and it doesn't matter which one you find first. Convention would be go x and then go y. So I'm going to do x-intercepts first. And so it's the same as usual. To find an x-intercept, you set y equal to 0, which means the same thing as setting the function equal to 0. But with a rational function, that will only happen if the numerator equals 0. So that means 2x equals 0, which just gives me x equals 0. So we have the point 0, 0. Now, we don't need to even find the y-intercept because we've already found it now. If you might notice that that's the origin, which means it's the only point that's both an x-intercept and a y-intercept. But just to make sure this is applicable to all situations, when you're looking back at your notes, I'm going to do the y-intercept work anyways. So f of 0 equals, this is a situation where the unfactored form is far more useful, because then all these just become zeros except for the -3. Whereas here, I'd have to plug in 0 times 0 minus 3 times 0 plus 1. You could do that. Nothing's stopping you, but it's faster to compute it in the unfactored form. So it'll be 0 over 0 minus 3. That's 0. So we have 0 comma 0. Any questions so far? Okay. We're going to find the asymptotes, and then we're going to leave. That's what we're going to leave off for today because of my whole thing with my sick son. So he's not doing. I mean, he says he's not doing well, but maybe he's not. Maybe he's being a little. Maybe he's selling it a little too much. But either way, I'm getting sidetracked. So we'll finish off this, and then we'll talk about how to graph them, and then we'll do the last 3 problems after this on Wednesday. So we're going to find all the asymptotes. The next thing, we found the intercepts, we found the domain. We need to find the asymptotes because if we want to draw this, we need to know where the asymptotes occur. So in terms of holes, there were none. From our pink note up above. For the VAs, we're going to set the denominator equal to 0. And so the denominator was x plus 3 times x minus 3, excuse me, x minus 3 times x plus 1 equals 0. And that gives me x equals 3 and -1. And yes, I know we already did that up above, but just so we see it in action here, because sometimes there's a new denominator equaling 0. And so those are our vertical asymptotes. And then HA, the horizontal asymptotes, look at degree. The degree of the numerator is 1. The degree of the denominator is 2. So the degree of the numerator is smaller, is less than the degree of the denominator. So there is a horizontal asymptote at 0. The degree of the numerator is less than the degree of the denominator, which implies an HA at y equals 0. I'm underlining all the pieces of information that we're going to need to graph this. We're going to need this and a little bit extra, and I'll explain that in a little bit when we come back on Wednesday. But I think this is a good stopping point for now, especially since, this will be a good stopping point. Are there any questions on this before we call it good for today? I'm sorry about the abrupt cancelization. This was not intended. He woke up with a very, very bad cough, and so I need to trade off with my wife so that she can get to work. Any questions? Okay, guys, that'll do it for today. We'll pick up on Wednesday and finish off Unit 2 as long as everything goes according to plan. I will be opening up the homework sets very, very soon, as soon as I get a chance to. And that way, if you miss anything, you can get free practice and also get free points, essentially. It's a win-win. Yes, specifically for this unit. So for Unit 2.
I think almost for Unit 1.
Yeah, sure. That's fine. All right, guys, that'll do it for today. If you have any questions, email me or come to my office hours.